Greetings of the day, one and all. I am VNSUV Ammu from JNARDDC. I am giving a brief presentation on the topic die design modifications for uniform profile quality in aluminum extrusion using numerical simulations. This is a brief outline of my presentation about JNARDDC and our domains of expertise in aluminum extrusion, applications of aluminum extruded profiles and demand drivers. I am also going to talk about the overall process flow for aluminum extrusion, factors affecting the quality and numerical simulation approach, metal flow in aluminum extrusion and also the case studies. About JNARDDC, JNARDDC is recognized as Scientific and Industrial Research Organization by the Department of Scientific and Industrial Research, Ministry of Science and Technology, Government of India. It is the only institute of its kind in India pursuing the cause of R&D from bauxite to finished product under one roof. JNARDDC was established in 1989 as a joint venture between Ministry of Mines, Government of India and United Nations Development Programme. Our expertise in aluminum extrusion is like this: raw material. For extrusion, it is the billet. We characterize its chemical composition microstructure using high-end OES and optical and SEM microscopes. Die design and simulations, we take up numerical simulation studies on dies for uniform profile quality using hyper extrude and deform. And also we design dies for various profiles. Extrusion, we carry out extrusion for validation of new dies, new profiles and also for process optimization using our 14mm extrusion press. And also we do anodization studies on various profiles and also characterization of extruded profiles by mechanical testing and microscopy techniques. There are various kinds of aluminum extrusions used for different applications from home to space. That is, aluminum extrusions are used in automobile and also building and construction, transportation, industrial design, energy and also HVAC applications. When it comes to the advantages of aluminum extrusion is most cost effective and quickest path between concept and the product. Aluminum metal and extrusion process both together yields excellent results in terms of form, fit, function, appearance and produces cost effective parts. Near net shape process that can produce close tolerances. Aluminum extrusions are green, produces strong and lightweight designs that are fully recyclable. Thermal conductivity of extruded profiles are comparable with pure aluminum, and aluminum itself is highly thermally conductive, that is, it is most widely used for heat transfer kind of applications. In this diagram, we can observe various complex shapes can be realized by aluminum extrusion process. We can observe fins with high heat dissipation characteristics can be produced. Also, complex shape production is possible by using an appropriate aluminum alloy. There is a scope for extensive use of aluminum extrusions in various fields. In building and construction, more scope exists for wider sections and more complex shapes. Load-bearing sections needs to be produced with tighter tolerances. In other sectors with growing demands of energy requirements, solar panel and lightweight structural applications, huge demand can be expected. In automobile sector, heat transfer sections such as condenser pipes will be in demand. In industrial sector, motor casing, heat sink profiles and marine and structural applications will be the drivers of demand in future. The raw material for extrusion is produced by billet casting process in the form of cylindrical billets. Further, these billets are subjected to homogenization treatment, preheating of billets prior to extrusion followed by extrusion and press punching and heat treatment for producing various tempers. Aluminum extrusion is a thermomechanical process where strain, strain rate and temperature are major process variables. The finish, quality and productivity of profile depends on efficient operation of process variables. Billet is transformed into the final product by application of large amount of forces and heat. Heat transfer and deformation friction at various interfaces influence product quality. Also, the dies and tooling needs to sustain high thermal stresses and extrusion loads. Critical areas or thin sections in the dies needs to be controlled or supported. Die design controls the metal flow. There are three major factors affecting the quality of extruded profiles. Billet quality, the homogenization and chemical composition of the billet, influence the flow stress of the material, and also the process parameters, billet, container, die temperatures, ram speed, friction and lubrication at various interfaces. Coming to the die design, extrusion ratio, geometry variables in the die, extrusion pressure or load are the major parameters. Various researchers have carried out studies on metal flow during aluminum extrusion process using different techniques. Three cases have been represented here, with case A has no or minimum billet container friction and case C with maximum friction at billet container interface. Case B is intermediate friction conditions. Metal flow during extrusion is a cylindrical flow with maximum velocity occurring at the center during extrusion. It is being represented schematically. The length of arrow represents velocity. Higher arrow length indicates higher velocity. Also, dead metal zones gets formed near to the die exit. Operating window for aluminum extrusion is majorly influenced by productivity and press exit temperature of profile. Every extruder will try to push billets with maximum speed. However, due to extrusion ratio, alloy characteristics and also the product exit temperature will limit the maximum speed that can be achieved. Maximum pressure achievable will also be limited due to the factors mentioned above. In this regard, an operating window for each alloy with different extrusion ratios has been worked out. In this slide, I am going to explain the extrudability of different aluminum alloys. Extrudability is the relative ease with which extrusion can be carried out. Extrudability equal to and above 100 are easy to extrude alloys. Those are low strength alloys, 1 series and 3 series alloys. Alloys with extrudability between 50 and 100 are medium strength alloys. Those are 5 series and 6 series alloys. Those with extrudability below 50 are difficult to extrude. Those are 2 series and 7 series alloys. The table indicates the extrusion of various alloys using the press available at JNARDDC. AA6063 has got highest extrudability, and you can observe the extrudability of other alloys have been rated with respect to 6063. 7075 has lowest extrudability, that is 10, and 2024 has slightly higher than 7075 extrudability, that is 15. 6082 has lower extrudability than 6063. 3103 also has higher extrudability than 6082. In this slide, I am going to show the classification of extruded profiles depending upon whether it is flat profile or hollow profile. The flat profiles has no enclosed volumes and relatively simple to extrude. Hollow profiles has enclosed volume and difficult to extrude. Almost all aluminum alloys can be produced in flat configurations, but for hollow profiles production, the typical alloy should contain relatively less alloying content and ease of welding. This slide is showing the die configurations used for producing solid profiles and hollow profiles. And solid dies has got the configuration of die with bearing length, and porthole dies have got a split die, that is upper die and lower die, and this has got various geometric configurations that has to be closely controlled to obtain good quality extruded product. This slide is showing the solid die design of bearing lengths. In solid dies, bearing lengths are used as shape forming areas to control metal flow by artificially inducing or reducing the friction. In the figure, the red portion indicates the bearings. In the initial design, uniform bearings have been used throughout. However, the metal flow was non-uniform. In the second figure, the bearing lengths have been varied to control and produce uniform metal flow. Also, figure indicates bearing lengths are kept on the billet side so that billet comes in contact with the bearing lengths and deforms. Section DD indicates stepwise linear variation of bearing lengths, which is used in the shop floor. This slide is showing the metal flow in porthole die. The complexity of this die is relatively higher compared to the solid die. In this, metal splits and enters the portholes and gets welded inside the weld chamber under the influence of high pressure and temperature. The shape of ports, weld chamber and also the bearing length and mandrel influence the product quality. This slide is talking about the die design in the conventional approach. In the conventional approach, die design is very hardware intensive and it is very expensive and unreliable because of the judgment of operators, and it takes longer time for development, And also the die life prediction is not possible. Product quality cannot be predicted prior to extrusion, and in it the implicit knowledge of operators or fabricators are important, and the knowledge is not explicit. Numerical simulation approach for die design. The component alloy will be defined by the end user requirements, aluminum alloy material properties, die design engineering, etc. to be integrated by product process integration. Finally, limited validation trials are required for saving the productivity and time required by the machine. Flow stress curve and material properties. The alloy deformation characteristics are mathematically represented by the flow stress curve. Using these material constants, various flow stress can be generated and relative extrudability can also be estimated. This data is very important for the numerical simulations. Various ratios have been explained here: the extrusion ratio, the extrusion speed, and the equivalent diameter of extruded profile, and the average strain and strain rate can also be derived from these equations, and these equations are important for estimating the product exit temperature of the profile. This is a typical case studies used on the display profile. The profile is used for general architectural purposes. The die is two parts, die mandrel and die cap. Die mandrel has got 5 mandrels and the die cap is designed with 4 ports. This study is aimed at optimizing the die geometry parameters to produce a defect-free product. This slide represents the flow stress data used for AA6063 alloy. For numerical simulations, the mathematical expression used is the sine hyperbolic law and can be used for all aluminum alloys. Z is Jenner-Holoman parameter, epsilon prime is the strain rate, delta H is the activation energy and generally depends on the alloy. G is the universal gas constant, T is the temperature of extrusion, and A is the reciprocal strain factor and N is a constant. For this simulation, the boundary conditions used for numerical simulations are shown here. The ram is pushing the billet with constant velocity and billet is maintained at the container temperature. There are different interface frictions at billet container wall and also it induces the heat generation. Product experiences friction drag due to friction at bearing, which is also contributes the temperature rise of profile. Profile is cooled by free convection or forced convection, and profile moves with a velocity of ram times the extrusion ratio. Finally, there will be a net increase of temperature of profile. The process parameters used for simulations have been shown in this slide. Initially, the die design is based on the first principles and the die design has been improved with respect to different iterations depending upon the velocity and temperature profile which is obtained after the simulations. The process parameters used here are the billet diameter is having 7-inch billet and the billet length is about 300 mm, ram speed is 5 mm per second, billet temperature, initial billet temperature is 450 degrees centigrade, die temperature is 450 degrees centigrade, container is maintained at 420 degrees centigrade. So the final iterations have been stopped when we achieved the uniform profile velocity and also the uniform temperature distribution on the profile. Also in this slide I am showing the validation results. The nose piece of the profile indicates a very uniform profile output and also you can see the profile, and the die has got 3 parts. One is the mandrel, die cap, and also there is a small beaker that is used for this profile, and also the ram speed in the press trial and simulation result have been compared and it is almost comparable, and product exit temperature is also comparable. From these case studies, it can be summarized from the numerical simulation studies, load and temperature data predicted are comparable and also within the press capacity, and no surface defects have been produced on the profile by observing the profile. This slide shows the challenges faced during extrusion of different alloys. Process temperatures such as billet preheat, die, container temperatures to be closely controlled for good quality profile. Deformation heat generation, product exit temperature are closely related. Higher extrusion ratios will produce higher product exit temperature and also prompt for surface defects. Extrusion ratios combined with higher strain rates will produce defects, especially in alloys with lower extrudability. In high strength alloys such as AA7075 and 2024, the extrusion ratios and strain rates achievable are limited due to the onset of surface defects and also limitation of extruding within the available press capacity. Complex shapes can be easily achieved by alloys with higher extrudability. Profiles should be free from die lines, surface cracks and blisters, etc. The figures indicated huge temperature drop during extrusion for a profile, and we had to call off the trials in the middle. Speed cracking defects have been shown for two profiles during extrusion. The facilities available at JNARDDC has been put in this slide. We have got CATIA software for solid modeling of the dies. This is the input software for giving the die geometries, inputting the die geometries for the various simulation software such as HyperExtrude and Deform. And we have got two simulation softwares. One is the HyperExtrude for simulation and analysis of extrusion, and also Deform can be used. Both have got their own advantages and disadvantages, and it can be used as a complementary for carrying out various kinds of analysis. The slide indicates various dies designed, developed and validated at JNARDDC. Die set 1 represents the die of asymmetric profile used for building and construction applications. Die set 2 is the die of an architectural profile. Die set 3 is an industrial profile. The profile 3 is very complex due to the lower thickness in the middle compared to the edges, due to which the portholes had to be redesigned and modified to achieve uniform metal flow at exit. This slide indicates the extrusion press facilities available at JNARDDC. Our press is having a capacity of 14 meganewton, and it is having a container size of 6 inch and 800 billet size can be accommodated. It has got two zone independent heating zones inside the container, and also closed loop ram speed control can be achieved in this press. Also isothermal and isobaric extrusion can be achieved in this press, and it is equipped with inline quenching system. Using this press, end-to-end technology can be developed for various extrusion profiles, die design for critical profiles by simulation studies, and prototype component production can be taken up at JNRDC, and we have also got recently one project with Ministry of Mines for development of bus seating profiles for passenger bus applications. Various characterization studies carried out on the extruded has been shown in this slide. First is the visual inspection, where the surface defects of the profiles are captured using the naked eye, and second is the macro and microstructure observations on the extrudeds by using optical microscope and scanning electron microscope. And also we carry out mechanical testing on extrudeds for evaluating the mechanical properties of the extrudeds, and also we can carry out the non-destructive testing methods for identifying the flaws in the billets and products. Also, the facilities available at JNARDDC is a scanning electron microscope. It is extensively used for characterization of billets and the amount of precipitates and other their characteristics, and also the metallurgical microscope. Chemical composition by high-end optical emission spectrometer can also be used, and a universal testing machine is extensively used for generating the flow stress data for different aluminum alloys, and some of these facilities are NABL accredited. We also got studies on post-finishing operations like anodization and color anodization. We have got anodization setup to study the anodization for different aluminum alloys. JNARDDC for academic institutes. Joint research projects can be carried out with JNARDDC, MTech and BTech project work for students, vocational training for students, educational visits, and we also conduct workshops and seminars for students, and we also offer testing services for the benefit of students. The funding from Ministry of Mines, Government of India for carrying out research activities related to extrusion and also pilot scale facilities under one roof is gratefully acknowledged. Thank you for your patient listening. You can write to us in the email ID mentioned for any collaborative works, development of new profiles and designs for industrial applications. The pilot scale facilities at JNARDDC are developed as national facility for the benefit of Indian aluminum industry. You can also visit our website www.jnaRddc.gov.in and contact us. Thank you.